Hello and welcome back to another VMK in the game development series. In this VMK we're going to take our parser that we developed in the previous couple VMKs and import it into our game engine. Now this is going to be a lot of work because there's a lot of connections that we need to make. In our previous project that we created for the parser, everything was sort of standalone and inside its own project. Well, now we need to adhere to our game engine. So we need to make sure we make all the linkages with the proper containers when we're loading things, as well as making sure that we test properly for any error conditions that may occur inside of the file which we're parsing. Whereas before, what we did is we just returned, I think it was -1 whenever there's an error, but now we have to do something smart whenever we find that an error has occurred. If you're finding my videos helpful and you can support my website, please do so by clicking on the PayPal icon or by clicking on any of the Google ads found on the side. You can also purchase a membership through the link here, and that'll also help me out to keep my website up and running. Alright, back inside Visual Studio here, let's first take a look inside of our scene. And inside of our initialize, you can see here what we have. We have our headlight, and we've defined a spotlight which we were using to attach to our cylinder that was rolling on the screen before. Then we also have our load textures, load materials, load geometries, and then we have the construction of the scene graph down here. Well, now what we're going to do is we're going to use the parser to automatically create all of this structure for us whenever it loads in the LVL file and then determines what it is that we need to have inside of the game. So what we can do is go in here and actually delete all of this code out, and we're going to write a function that will automate the process for us. So just scroll up to here. I'm going to delete it all the way up to here, and we'll call a function down here that will create the scene graph. So I'll just put here create scene graph structure. And what else? Oh, instead of loading textures will be done inside of our parser. So we don't need that here. However, we do still need to have a load font section because we didn't allow the user to specify how to parse font data to be loaded into our game engine. So that still has to be done inside of our code here. Everything else can be done inside of our parser, which will go down here. We're also going to delete the spotlight here since we now know how to load in light sources. However, we didn't specify how to load in a headlight. So I'm going to leave the headlight code up above here just the way we've done it before. Okay? Now the new function which we're going to be adding in this video, I've named it load level, and you pass into it one variable. So here I'm passing in testing.lvl, but this could be whatever you like. And as a matter of fact, you can make this dynamic depending on how you want to use this. But for now, we're just going to assume that the user is going to be responsible for creating a file called LVL, or testing.lvl, and inside here we'll have all of the code that we want this game engine to parse. Okay, so let's go into our scene.h file and define this guy, scene.h. And let's see here. We'll put it here, functions to interact with scene graph. Like so. And, well, we might as well go in and start implementing this load level function. Actually, you know what? I'm going to rename this to be SZ level file, just to be a little bit more descriptive. Now we'll put this function right above initialize. So here's initialize, and just above it, here's our load level. You'll recognize this load level function because it'll look a lot like the main function we wrote inside of the parser project which I showed in the previous videos. There have been a few modifications to it so that it will work properly with our game engine. So what I would actually recommend you do when you're watching this video is go back into your code that you had from the previous video, the parser.cpp file, print it out, and keep a copy of that beside you so that as we're programming the code now inside of the game engine here, you can reference our original code to see where all these function calls are coming from. I'm not going to be going back and forth between the previous project and our game engine because that would be too much work. Instead, I'm just going to be pasting in code directly into our game engine. I'm going to assume you already understand the structure of the parser. So first thing we do here is we check to make sure that the parameter that's passed into this function is not equal to null. If it is null, then that means we can't load in anything because we don't have a file name specified. So we're just going to return out of this function. We then go and create this file pointer again, and this file pointer this time is going to load in whatever is passed into here as a text file, and we specify here that we're going to be reading it. We check to see if our file pointer is valid. If it's not, we use our error handler this time to specify cannot find the file specified here. We display that error message, and then we reset the error code to be no error, and then we return. So this load level file could possibly give us an error saying couldn't find whatever we wanted to parse. We create this SZData parameter once again, and this is going to be holding one line of string from the file that we're parsing. So let me comment this in here. And line max length needs to also be defined for us. So we're going to go inside of our scene.h file here, and right at the top here, let's go and define it. Just like before, we're going to set it to be equal to 300. However, if you are customizing your parsers, you may need to up this value here in case you do have long strings passed in. Okay. Now, here's two new variables that I create. There's one called vLevelParam and vNodeID. And initially I clear these. So let's go into the scene.h file and define what these are. I'm going to do that down here. All scenegraph nodes. Let's do it right above that. So here we go. Our first parameter is an std vector of level file param. And we haven't defined this yet, so you won't know what this is. And the second guy is an std vector of unsigned int. Now, let me go define what level file param is, and then we'll come back here and I'll describe to you what each of these parameters or variables are actually used for. So scrolling back up to here, structures are defined below, so let's go and define these. Okay, here's our structure for level file param, and it will contain an integer, which is an ID number. It's going to contain a parameter type, which is defined up here. It's going to be one of these, and it's also going to contain an unsigned integer, which is called UIID. Now, what is this thing, and why do we need it? Well, as a matter of fact, if you remember back to how the LVL file is structured, the user is responsible for providing GeoID, texture ID, texture transform ID, and I don't remember if there's another one. But basically, those are ID numbers that the user has specified so that when they want to use, for instance, a texture, then inside of the LVL file, they can associate this specific shape is supposed to be attached to this specific texture. Now, you'll remember that inside of the game engine, we also have a similar structure using the ID numbers. But the ID numbers that the game engine creates will not be the same ID numbers that the user specifies, because it's actually dependent on the order in which the game engine creates them. So what we need to do here is create a relationship between the user specified ID numbers with the ID numbers that the game engine creates. So these are what these two values are going to be holding. And this extra parameter here, parameter type, is going to be telling me what kind of ID number is this current object storing. Is it a geometry ID? Is it a material ID? Is it a texture ID? Or is it a texture transform ID? Those are the 4 different ID numbers that the user can specify inside the LVL file, and those are the 4 different kinds of ID numbers that the game engine will be using. So this structure is basically like a lookup table that will look up what user number the user specified and what number does the game engine actually use. You'll see this being used in a minute once we go into our code, but just sort of understand what this is for. Up here you'll also notice that I included the return type, which we used inside of the Parser project. So we have our char, int, float, float array 2, float array 3, float array 4, and we also have our return error codes, the OK, error duplicate, not found, and no value. I don't remember if I swapped these values around compared to our previous project, but just double check to make sure that inside of the game engine this is the order of these return values that we're going to be using, and again these may be in a different order inside of the Parser project. So going back here now, where were those parameters? Here they are. Okay, so we're creating a vector of those values. So remember, this parameter here is for a structure that contains a relationship between a user-specified ID number, ID type, and the game engine ID number. So that's what that is, and this is an array, so we actually create a table for all those values. This parameter here is a structure that we need so that we can associate objects with other objects, or in other words, we can nest them. As we're creating objects inside of our game engine, we need to keep a history of what was at level 0, what was at level 1, what was at level 2, so that when we do nest them, we know how to reference back to the ID numbers, because that's what the game engine needs to use whenever we're calling add node or assign texture and so on. All of these require ID numbers for referencing one object to another, and those ID numbers are going to be stored inside of this vector here. And again, you'll see in a minute how we use this, so don't worry too much if you don't quite understand what I mean right now. It'll be more clear once we go into the code. Okay, so back here, at the very beginning of the load level function, what we do is we clear out both of those variables, and both of these variables are arrays, which contain basically nothing once we clear them all out. First thing we do is we define our iLine value to be 0, so we know which line number we're going to be parsing. And again, we go and get the first line of text, we increment the line number, and we do some error checking to make sure that the line isn't too small. The line, if it has comments, we can just skip over it. If it has the keyword end, then we just quit parsing. And we also check for errors to see if the length of the line is less than 9. If it is, we generate an error message, and we continue on through. Otherwise, we'll call parseLine. And parseLine is that special function which will go and parse the line of text which this guy here retrieved for us, and inside here we will handle all the construction of the scene graph automatically. Once we leave this while loop here, we're basically done parsing, so we can close the file that we're loading all the data from, the LVL file. We can close that off, and we can go and clear the 2 parameters here which we just defined. We won't need them beyond our load level function because these are just helper variables, but beyond that, once we've loaded everything and created the scene graph, we don't need these anymore. So we can go and clear them just to save some memory. Okay, so now we have to go inside and define parseLine. So back inside scene.h here, we'll go right underneath load level and specify parseLine is going to be a function that doesn't return anything, and it's going to retrieve 2 parameters. It's going to take the line of text that we're going to be parsing and the current line number. we need this line number here so that when we generate error messages, we can specify on which line error occurred. Okay, so now let's go and implement this parse line function. And we're going to put it, let's put it right above, actually let's put it above load level because it makes more sense that for it to go there. Now this function is humongous. It's about 1,400 lines of code because there's actually a lot of details we need to take care of. So you'll notice it's a lot bigger than our previous project's parse line function, but that's because now there's a lot more work being done. So make sure that you're referencing our previous code from the parser.cpp file when you're looking at this code. I'm not going to try to go through all the details that I covered before. I'm just going to cover all the new stuff to make it work inside of the game engine. Okay, so here we are. We have parse line. Take one line of text from the level file and decide what data it holds and what to do with it to make it work inside of the scene graph. So once again, we're passing in a line of text that we're going to be parsing and which line number this line of text came from. We create a variable here that's 25 characters long, and this is going to contain the current keyword that we're looking for. We also have a variable here called return code, which will be used to determine how we want a function to return. So I just create a variable up here. We also create a variable here called param that is going to contain a level file param. And this here is that special structure that I talked about earlier. It's going to contain a ID number that the user wants to use for these geometry, material, texture transforms. It's going to contain what kind of type, so which of these the user wants, as well as what is the game engine's equivalent ID number for this specific user ID number. So I create that variable here. Now you'll notice that this structure is basically the same as what we had before. We have our if statement to check to see if the beginning of the string here that is passed in starts with box, cylinder, grid, material, texture, transform, shape, light, or the plus sign. If it's not one of these, we then just say unrecognized keyword on the specified line, and we display that error message to the screen, and then we return. Otherwise, it gets parsed in here, and then we'll go down here and just return normally. So let's start off with the box, since it's sort of the easiest guy. What we do is we first create a couple variables that contain all the required information to generate a box. So we're going to need the ID number, we're going to need the width, the depth, and the height. So the first thing we do is we specify that the keyword that we're going to be looking for is GeoID. So sprintf, what this does is it's going to take GeoID and dump this into our sz keyword variable. Then we call find keyword. We specify this is the keyword we want to find, and we're going to pass in all the same stuff we did before in the previous project, and we're going to check to see if it doesn't return OK. If it doesn't return OK, we know that this is bad because this is a required field for a box. So we generate an error message saying did not find this specified keyword on line, whatever line we're on. We generate the error message, we show it to the screen, and then we reset the error. And then we just return. If this is OK, then we go down here. We then test to see if the geometry ID number is unique. Now, inside of the LVL file, you can have multiple boxes and multiple cylinders and multiple grids and so on. And each of those have to have a unique ID number, or else the parser will get confused in terms of when you want to associate a shape with box GeoID number 1, is it the first GeoID number 1 that you specified, or is it the second GeoID number 1 that you specified? So to prevent that from happening, you must make sure that all the ID numbers inside of the file are unique. As a matter of fact, let's go into, well, I guess I didn't attach an LVL file into this project. Well, let's go do that, because then the discussion of how this parser is working may be a little bit easier to understand. So inside of our Visual Studio Projects game engine, underneath the build directory here, you'll find a debug, and inside debug here, I just created the testing.lvl file. So inside of our code here, we can now attach that LVL file as a resource file. Just right-click, click Add, Add New Item. Oh, sorry, not Add New Item, Add an existing item. Build, debug, and here's our testing.lvl. So inside here, this is just a sample file that has a bunch of different scenarios that we can parse. And you can notice here at the top we have all our objects. So we have GeoID _1, _2, _3, _5. Now when you're creating any sort of structure, make sure that all the ID numbers are unique. So you can't have two guys named number 1, because the parser is going to get confused. It won't know which ID number is associated with 1. So make sure that all of these guys are unique. And to make sure of that, inside here, this is where we're going to test to make sure that the GeoID number is unique. So we create a variable called bFound. We initially set it to false. Then we go inside of our member variable called LLevelParam. And remember, this is the guy that has that table structure to compare the user ID numbers with the ID numbers that the game engine is using. We're going to go through the entire structure here. So in other words, we're going to go through the entire array that's containing everything in here. And we're going to be looking for everything that contains GeoIDs. So we're checking the type parameter to make sure it's set to parameter geometry ID. And for every time we find one, we check to see if the user ID here is equal to the ID number that was returned to us from the find keyword function. This is a little bit different than how we handled things before inside of the parser project, because the find keyword function didn't have this fourth parameter. We added this fourth parameter, and what this does is we pass in a value into here. It's actually a void pointer that gets passed into this function, and this guy here is going to return to us whatever value we're looking for. So here we specify, please return to us an integer, and we pass in an integer parameter into here, so that when this function returns, we can then use the value that's stored inside of this parameter here and compare it with whatever we need to do. So I'll talk about find keyword in a second. Let me just go finish off this discussion here. So what we're doing is we're checking to see if the user ID inside of the structure is equal to the parameter that was just returned to us from find keyword. If these are equal, then that means that the ID number is not unique. So we set bFound equal to true, and then we break out of this for loop. Otherwise, we're just going to continue looping through, and if we don't find anything, then bFound is going to be equal to false. If bFound is equal to true, then we generate an error message saying that this specific keyword and the specific ID number that was passed in here was used more than once. Therefore, we generate an error on this specific line, re-show the message to the screen. If we get down to here, we know that the ID number that was found is unique, so we can continue on forward. And of course, initially, whenever you're starting off, this parameter here is cleared, so it doesn't contain anything, which means that the first time through when we do this keyword search, we're going to find an ID number, but then we're not even going to go inside of this for loop, because the size of this v-level param is going to be equal to 0. So that means that there isn't anything stored in here, so we can safely skip over this and just continue on through. You'll see when we actually save stuff inside of this parameter down below when we're done parsing the line of text that contains all the box information. Okay? Okay, so let me go finish off the discussion of how we parse the individual pieces, and then we'll come back to how find keyword works, because it has changed slightly. Okay, so once we find the required field, we then go looking for the optional parameters. and again we specify what parameter we're looking for. So the first one we're looking for is the width. We again pass in the width into the find keyword function here, and this time we're saying we want to return a float, so we're passing in the address of our floating point number that we want returned to us. And we do a check for the return code here. The find keyword is returning a code to us that tells us whether it found this specific keyword or whether there was an error or anything like that. So if the return code is equal to return error duplicate, then we generate an error message saying that this keyword was found more than once on this specific line inside of our parser. So this would happen if, for instance, here we had something like this. We had width underscore 0.35, and then on the same line of text we also had width equals 0.2. So if this occurs, we have this keyword found on the line of text twice. And that's actually bad because, again, the parser doesn't know which width you want to use. So to prevent that from happening, we check to make sure that we don't return duplicate values. If it's not duplicate, we then check to see if the return code is greater than or equal to not found. And if we go back into here, you'll notice that not found is equal to 2, and greater than not found would be no value. So if it's either of these, that means there was no width parameter passed into us, so that means we need to use the default. And the default, according to the PDF document, says that the width is set to equal to 1. So we take the f width value and we automatically change it to be equal to 1. If it returned OK, it's not going to go into either of these, so we keep the width value that was returned to us from our find keyword function. Alright, and then we just repeat. We do the same thing for depth, and there we go here. We pass in the address for the depth parameter. We check for duplications. We check to see if it's not found, and then if it's not found, we set to use the default value. Same thing for height. We pass in the address of the height parameter, check for duplicates, check if not found, use the default. Alright, after this we have all the parameters that we need to create our box geometry. So that's what we do here. We create a pointer to a geometry box, since that's what we're going to be creating. We call the new operator, and we're passing into the constructor the width, the depth, and the height. These are the three values that were either returned to us from the find keyword or set by our function automatically to the default values. If this returns correctly, then what we do is we take the user ID value and we save it inside of the param structure. Now remember here, right at the very top, we created this param that is of level file param. So we're taking the user ID part of this param structure, and we're saving the ID number that was returned to us from up above. We're saving that this type is a geometry ID, and we're also going to be saving the ID number that the game engine is going to be using. And that ID number is returned to us automatically whenever we call save geometry. So we call save geometry, and we pass into it the pointer to our geometry, which was created up here up above. So this function is a function that we wrote a long time ago that basically takes any geometry and saves it inside of our container for our game engine to use later. It returns to us an ID number so that we can reference this geometry whenever we need to. So we're taking that ID number and storing it inside this parameter. Once we have these three values saved, we then go and push those values onto our array stack so that they're saved inside of our member variable. Once we have them saved, we can then reference them anytime we need to inside of our function here to check for uniqueness of the geometry ID. Okay, so that's basically how the box structure works. And you'll notice that the cylinder and the grid are basically this exact same code, just for different parameters that each of these guys need to use. So before we go and talk about those, let's now go and describe this find keyword function. First, let's go into the scene.h and define the prototype for that function, which we'll put right in here. And okay, let's see. The first parameter we pass in is the keyword that we're going to be looking for. So this is the option. The second parameter is the string of text that we're going to be parsing. And then we have our return type that we're going to be expecting to receive. So this is going to say whether it's an integer, whether it's a float, whether it's a char, whatever. And the last parameter is a void pointer to pdata. And this guy is the actual address of the memory space that we want to return the appropriate values that we're looking for from this line of text that we're parsing. So if here we specify we want to return an integer, then this would be a pointer to an integer. If here we specify we want to return a float array of 3, then this is going to be a pointer to a float that contains 3 values. So this is why we need to use a void pointer here, because we want to use this function for many different reasons. Like we want to use it for integers, we want to use it for floats, we want to use it for everything. Because of that, we can't hard code exactly which pointer we want to point to. Instead, we use void pointer, and then inside of our function we can cast this guy to whichever appropriate structure we need to use. You'll see this in a second. So let's now go back inside scene.cpp, and right above parse line, let's go implement that function. Okay. So again, we're passing in the keyword, the data, the type, and the parameter, which is a pointer to a void. At the top, we're creating a couple of variables here, and these are the same ones we used before in the previous project, which will contain index values to where we are inside of this std string, so that when we're parsing it, we know how to find appropriate pieces. This stuff here is all basically all the same. We're looking to see if we find the keyword, we find the space at the end of the keyword, and then we have a switch structure to determine which parts are we expected to return. So are we returning a character string, are we returning an integer, a float, float array 2, array 3, array 4, and that's it. So if it's a character string that we're returning, what we do is we take the pdata parameter that was passed in as the fourth parameter into this function, and we cast it to a character pointer. And we save that equal to this local variable here, szname. We clear this guy's memory space so that it contains all zeros. And then we call sscanf. We parse this string of text again up to 255 characters, but this time we're saving it directly inside szname. And if it's not equal to 1, then we know that there's an error message, so we just return no value. Otherwise, we just break out because we're done collecting the string. For an integer, we take the parameter that was passed into this function, cast it as an integer pointer, save it into this guy's pointer value here, and then we're taking the atoi function, which converts this string of text, which should be a string of numbers, and we're saving it into the I value parameter, which is this guy here, under the index 0. So this guy is going to be now holding the integer value that was found inside of the string. Float, same sort of deal, but we're just casting it to a float pointer. Float array 2, same as float, but here you'll notice that inside sscanf, instead we see here we're using f2 values 0 and f2 values 1, because this is an array of 2 guys. And float array 3, similar thing here, we have 3% f's with 0, 1, and 2, because we're returning all 3 values. And the last one here, array of 4, which just has that extra fourth parameter tacked onto the end. Okay, so this should be very similar to what we had before. The only difference now is we're using a pointer here, which is containing the address of the variable that we're storing the number or the value that we're extracting from the parsing. Down at the end, we also have to check to see if we have any duplicates. So again, we just do the same thing we did previously in the parser project, and if b index is not found, so in other words, there is no other instance of this keyword or option, as you want to call it, then we just return OK. Otherwise, we return error duplicate. Okay, so that's it. Now we can go down into here and finish talking about how to implement these guys. Alright, so cylinder. We create some variables up here which will contain all the parameters that we need to create the cylinder inside of our game engine. So we have the GeoID, the number of sides, the radius, the height, and the smoothing parameter. First thing we look for, the required field, is the GeoID, and we expect to get an integer back from there. Similar to what we did with the box, we check to see if the GeoID number which was returned to us here is unique. So we do that using this for loop again. We loop through looking for all the GeoID parameters, and we compare the ID number with everything that's stored inside of that array. If it's not unique, we set b found equal to true, so that we go inside of this if statement down below to generate that, oh, there was a duplicate, and we write an error message on which line that was. Then we go and look for the optional parameters. So we look for the number of sides here, so we set the keyword to be num underscore. We are expecting to return an integer value, so we're passing in the address of the inum sides parameter. We handle duplications, and we handle the default value. So if it's not returned to us, or there's no value, then we set the number of sides to be equal to 20 by default. We check to see if there's a radius value. Here we're passing in the address of fradius. Looking for duplicates. If not found, we use the default radius value of 1. Check to see if we have smoothing turned on. So we're passing in the iSmooth parameter here, which is an integer, and check for duplication again, and then if it's not found inside of the keyword here, then we set the smoothing to be turned on by default. So we set it to be equal to 1. Last parameter is our height. So we pass in fHeight here and handle duplication and set the default of height equal to 1. Once we have all the parameters, we can then go and call geometry cylinder pointer. So we create a new geometry cylinder and we pass in those 4 parameters. Now you'll notice that the last parameter is, for the constructor, is required to be a boolean. But because iSmooth up here returns an integer, I use the following code here to convert that integer to a true or false value. So we check to see if iSmooth is greater than 0.5. If it is, then that means we want to use smoothing, so I automatically pass in true. Otherwise, I pass in false. This is basically a compressed version of an if-else statement. If this evaluates to true, then it's going to return this value, and if this executes to false, then it's going to return this value. That's basically how that line of code there works. Then we check to see if the pGeometry pointer that was defined up here is valid. If it's not, we generate an error message saying, cannot create a new cylinder object. Otherwise, we'll go down here, and again, we need to save all these 3 values inside of this param structure. So we save the GeoID that the user specified. We say that this is going to be a geometry ID, so we save that as the type. And then we need to return the ID number that the game engine is using. So we call save geometry, pass in pGeometry from up here, and this guy is going to return to us an unsigned integer, which also gets saved inside param. Then we go and push that value back onto the stack here, so that now we have a storage of this instance inside memory. Okay, now we have the grid. Again, same sort of deal. We create memory here for the GeoID, the width, the depth, and the number of divisions in X and Z. We look for the required GeoID field. We check to see if the ID number that was returned to us from find keyword is unique. If it's not unique, we generate an error message. Then we look for the parameters, which are optional. Check for the width, which passes in the width parameter here. And if it's not found, we use the default of 1. We look for the depth. If it's not found, we use 1. We look for divisions in x. If it's not found, we use 1. And we also look for divisions in z. And if it's not found, it's also equal to 1. Then we go and call geometry flat grid using all the parameters that we found or the defaults. Then we go and save the user ID number that the user specified. The type again is GeoID, param_GeoID, and the ID number that the game engine returns to us whenever we call save geometry and we pass in pgeometry in here. And don't forget to save this parameter structure back inside of the array that's contained inside of the scene. Alright, so that was all the geometries that we're allowed to save. Now we can move on to the material. Okay. Once again, we create some variables that we'll need whenever we create the material node. So we're going to need a material ID, the ambient color, the diffuse color, specular color, and emissive color. All these colors are float arrays of 4. And we also have a standard float, which is going to contain the shininess. So first thing we look for is the material ID, because it's required. So we pass in the address of iMaterialID, and we check to see down here whether this ID number is unique. So same story as up here. Anytime you specify materials, all these ID numbers have to be unique. You can't have duplicates here. If we don't find any duplicates, we'll just continue on down here. And first thing we do is we create a new material node. So we create a pointer here to a material, so pMaterial, and we call new material. After we've created this new material, we then look for the optional parameters. You'll notice that this is slightly different than what we did with the geometry, and I'll tell you why we did this in 1 second. First thing we look for is the ambient color. So here we pass in, please return to us a float array of 4. So we pass in the address of the ambient color parameters first index. Then we check the return code. If it's a duplicate, we generate an error message, and we need to call safe delete pMaterial. Because we created it up here, if there's an error message, make sure you delete this, or else you'll have a memory leak. We didn't have to do this before, because anytime we did the find keyword, we didn't create the new geometry before. Whereas now we did create the new material, so we do need to delete it. Alright. If there is no duplication, we check to see if it's return equal to OK. If it is OK, that means that the value that was over here has something that was inside of the LVL file. So we want to take those 4 values that were returned to us and save them inside of the material that we just created up here. So we do that just by taking the ambient color, 0, 1, 2, and 3, and just saving those directly inside pMaterial. We don't need to take care of the default this time, because the default is set inside of the constructor for us. So this is another way of handling the default. Instead of writing the defaults automatically, we only write whenever we get a return value from our find keyword function. So next thing we do is we check the diffuse color. Once again, we say we want a float array of 4, so we pass in the address of the diffuse parameter, the 0 index, so the first guy, and then we check to see if the return code is equal to OK. If it is, we save it. Otherwise, we're just going to leave it, because the diffuse color is already set inside of the constructor to whatever the default's supposed to be. Specular color, same sort of deal. Again, we pass in the specular parameter in here, and if the return is OK, then we save the specular color that was returned to us inside of the pMaterial. Emissive, same thing. Say we want the emissive parameter in here, and then if it returns OK, just save it inside pMaterial. And then shine, same thing, but this time we just return a float, so we just pass in the address of the floating point number, and if it returns OK, we take the shininess value and save it inside of pMaterial. Okay, So now we have a valid p-material that has all the parameters that were saved inside of the file that we're parsing. So we can take that param structure and save the 3 parameters that we need. The material ID goes under user ID. The type is now param material ID, and the ID number that the game engine is going to be using is returned to us whenever we call save material, and we pass in the p material here. And then finally we just push that parameter onto our member variable, which is part of our scene. Okay, moving on to our texture transform. Once again, we have our parameters that we need for creating a texture transform node. First thing we do is we check for the required fields. So we have the texture transform ID number, which is required. So we pass in, we want to return an integer, and we're passing in the address of our texture transform ID. We check to see if there's any duplications of that texture transform ID number. So again, with texture transforms, I don't have any in this file, but if we did, all of the ID numbers would have to be unique. So that's what this here takes care of. And then we do the similar thing to the texture transform pointer as we did with the material pointer. We first create it up front. I called a new operator, so new texture transform. And then we go through looking for our optional parameters. So we look for scale, and here we have float array 2, so we pass in f2 scale, index 0, the address of. If there's an error code, make sure you call safe delete, or else there'll be a memory leak. Otherwise, we go and set the scale for 0 and 1 equal to the texture transforms scale 0 and scale 1. Check for rotation. Rotation is just a floating point number, so we pass the address of the floating point number. And if it returns OK, we just save that floating point number into our texture transform. We check for the center parameter. It's a float array of 2 this time. And if it returns OK, we just save it inside the texture transform. We also look for the translation value. It's also float array 2. And if it returns OK, we save it inside the texture transform pointer. And then lastly, we go and save the user ID number for the texture transform. We set the type to be param texture transform ID, and the game engine's ID number that it will use is returned to us whenever we call save texture transform, and we pass in our p texture transform that we defined up above. And then don't forget to push that new parameter into our member variable. Next, we have our texture. So we have a couple parameters here that we'll need whenever creating a texture node. We have texture ID, bitmap, quality factor, whether this texture is completely solid or whether it has alpha values. And then we have our file name that we're going to be using for the texture. We check the required fields first. So we require a texture ID number, and same story as before, all the texture ID numbers have to be unique, so you can't have something like this. This will generate an error. So make sure that all the ID numbers are unique in here, and down here we're going to confirm that all of them are unique, so we check to make sure that all the ID numbers that are stored are not the same as whatever is returned to us from the find keyword up here. So after we get the texture ID number, we then go down here and look for the other required field, which is the file, because we cannot create a texture inside our game engine without knowing which file we need to load. And again, I'll just remind you, anytime you use the file parameter, make sure that there's no spaces inside here. So don't put any spaces inside the directories where your TGA file may be sitting, because if you have a space in here, then the parser will not work properly. So we call find keyword. We want to return a character string, and we're passing in the address of our file name's index 0 parameter. If this returns OK, we can go down here and basically start looking for the optional parameters. Now you'll notice that I didn't go and call create new texture this time. like I did for the material and for the texture transform. Instead, I'm going to handle this similar to the way that I handle geometry. So first thing I look for is the mipmap parameter. And here we're saying we want an integer, so we're passing in the address of imipmap. Check for duplications, and if it's not found, we set the default value equal to 1 for the mipmap, which means we want to use mipmapping, because mipmapping is a boolean, which you'll see in a minute. We have the quality factor, which is an integer, so we pass in the address of iQuality. Check the return code. If it's not found, then we set the quality factor to the default of a value of 4. We check to see if a solid parameter, so we pass in iSolid here, and then for the return, we automatically set it to 1 if it wasn't found. Alright, once we have our parameters, we can then go and create a new texture. The way we do that is we use our constructor, texture, we pass in our error handler, and we need to pass in a couple parameters. First parameter is a boolean, so we need to convert our mipmap value to a true or false value. The way we do that is using this line of code right here. Check to see if the mipmap value is greater than 0.5. If it is, it's going to return true. Otherwise, it's going to return false. The quality factor is the third parameter that gets passed inside this constructor, but the quality factor has to be of type filter quality, which was an enumeration that we defined before. You'll notice here, where is it? Filter quality. So it has to be one of these. You'll notice that fQuality1 is equal to 0, this is equal to 1, this is equal to 2, and this is equal to 3. So what we really need to do here is, actually there's an error in this code here. We're passing in a quality factor which will be 1 through 4. However, the filter quality is only going from 0 to 3. So we can change this a number of ways, but the easiest way would be just to change the filter quality to start here at 1, so that anything that's inside of the LVL file will automatically correspond to the appropriate filter quality. So let's go and change that and move along. The next guy here is iSolid, and again it needs a true or false value inside of the constructor. So we check to see if iSolid is greater than 0.5. If it is, it'll return true. Otherwise, it'll return false. Then, let's see here. We check to see if we had enough memory. If not, we generate an error message. Otherwise, we created a texture and we're ready to go onward. So we go and save the 3 parameters that we need. We have the user ID number, which is iTextID. The type is param_texture_ID. And the game engine's ID number that we'll use for this texture will be returned to us when we call load texture. And when we call load texture, we need to pass into it a texture pointer here, as well as the file name. So this function here will do the loading of that specific file that we want to load. Then finally, we need to push that parameter onto our member variable, and we're done with the textures. Okay, next up is our transform. So we create some variables that we need to use when creating the transform node. So we have a name here, we have visibility, translation, center, scale, axis, and then angle. First thing that we do is create a pointer to the node transform. So we call the new operator for new node transform, and this will automatically fill in all the default values into the translate, center, scale, axis, and angle that is used by this node transform. Then we go and look for all the optional parameters. And you'll remember there is no required parameters for the node transform, because everything by default is perfectly valid. So we only look for optional parameters. We check to see if there's a keyword called name underscore. So we call find keyword, say we want to return a character string, and we pass in name index 0 here, and we pass the address of that guy in. If the return code says error duplicate, and we found more than one name on this line of text that we're parsing, so we just return an error message, and we need to call save delete because we created this new memory up here. Otherwise, if it returns OK, then we go and call setName for this node transform, and we pass in the name that was returned to us from our find keyword. So we automatically update the name of the node transform if we found it. If we didn't find it, then we don't need to set the name because we didn't have a name to use in the first place. Next thing we look for is visibility. So we pass in here, we want to return an integer, and we're passing in the address of iVisible. If it is returned to us OK, then we take the iVisible parameter, check to see if it's greater than 0.5. If it is, we return true. If it's not, we return false. And then that parameter gets saved inside of the node transforms bVisible parameter here. If there was an error again, because of duplication, don't forget to call save delete. We then check for the translation value. So this time we're looking for a float array of 3 values. So we pass in f3 translate, index 0, and the address of that. Checks for some errors, and if it returns OK, then that means we did have a translate. So we take the 3 parameters that the translate returned to us, and we're going to pass those into vector 3, which will then create a vector 3 for us, which we save directly inside of our node transform. We do the same thing for center. We pass in the center parameter, and if it's OK, we create a vector 3 using the 3 floats, and we save that inside of the node transform center. And same thing for scale. We pass in the scale parameter here, and if it's returned to us OK, then we pass in the scale into vector 3, which then gets saved inside the node transform. Axis, same thing again. Pass in the axis parameter here, and if it returned to us OK, we pass the axis values into vector 3, and then that gets saved inside of the node transforms v3 rotation axis. Last guy here is the angle, which is just a float, so we pass in the address of the float angle parameter, and if it returns OK, we take that angle and we save it inside of the node transform. The next section of code, shown down here, is a little bit tricky, so let's go into PaintShop Pro so that I can explain it visually. Alright, let's suppose that we have a tree structure that looks like this. At the root, we have a transform node, and then underneath that we nest another transform, and then underneath that we have a shape node. Then back out at the root, we have another transform node, and then again another nested transform under this one here, a shape, and then a second shape, but this shape is actually nested underneath this transform shown here. So how would this be represented inside of our text file? Well, it would look something like this. We place plus signs to indicate the nesting structure. So here we can see this transform. I might as well start numbering these so I can refer to them a little bit easier. Let's see here. This would be transform number 1. Then nested under transform 1 we have transform 2. And nested under transform 2 we have shape number 1. Then also at the root we have transform number 3. And nested under transform number 3, we have transform number 4. You can see here that the pluses indicate the nesting structure. So if we have 1 plus sign, that nests underneath this one. 2 plus signs nest underneath the one that has only 1 plus sign. So down here we have 2 plus signs indicating shape number 2 is nested under this one here, which is transform number 4. And then shape number 3 has 1 plus sign, which means it's nested under the transform that has no plus signs, which is this one here. Now the way that we're going to figure out all this nesting structure is we create an array, and the array is called m_vNodeID. And this array initially is empty, so we don't have anything in here because we haven't worked with anything to do with the nesting structure. So as soon as we come to the very first transform here, what we're going to do is we're going to look inside of this array and say, okay, is there anything stored inside here? Well, initially there isn't, so what we have to do is we have to call push underscore back, and we specify what we're going to be pushing back inside the brackets. And this array is going to hold the unsigned integer ID numbers for each of these objects that are stored inside of the tree. So whenever we finish creating transform 1, we're going to store the transform 1's ID number inside this location here in the array. Then we're going to go down to transform number 2. Once we're down at transform number 2, we go back into this array and we say, okay, now let's take a look at this location here. The index values for this array are indexed from 0. So this would be 0, this would be 1, 2, 3, 4, and so on. So we know that transform number 2 has one plus sign, which means it's nested underneath this guy here. Well, if we look inside of this array here, at location 1, we currently have nothing. So transform number 2 will be saved in this location. And we know that it's nested under whatever is located at node number 0, which is transform 1. Then we're going to go down to shape 1. Well, we have two plus signs, so the shape value, the shape ID value is going to get stored in here under ID number 2, and we're going to know it's nested under whatever's saved under node number 1, which is transform number 2. Then when we get to here, transform number 3, we're going to go back inside here and say, okay, we look at this array and we see that this time we have something already stored at node 0. So instead of pushing back, we don't push back this time, because pushing back basically adds it to the very end. Instead, we're going to go in and replace the value that's stored at number 0, because transform number 3 is actually stored at the root, which has no plus signs here. So it gets saved inside of this array at index number 0. So it's going to go right here, transform number 3. Then when we go to transform number 4, it has one plus sign, so it's going to get replaced inside here. So instead of T2, we're now going to have T4. And we can look back at node number 0 to see it's supposed to be nested underneath T3. Shape 2 is going to replace shape 1 here. So we have shape 2. And then you'll notice here that when we get to shape 3, we have one plus sign. So we're going to go looking here. We're going to see that there's already something stored here. So we're going to replace this guy with shape 3. And by looking at the one above it, we know that shape 3 is nested under transform number 3. And if we look back here, we see that makes sense because we have one plus sign, which means it's stored underneath transform 3. So the way that we save this tree structure will be saved inside of this array. And this array will help us to identify what is nested under what whenever we need to create the scene graph. So that's how it's all going to work. Now let's go into the code and see how to implement this. We finished here, what did we just finish doing? We scroll up to the top, we see we're working with the transform node, and it's located at the root. So we scroll down here, and we created the pointer to this p node transform. And now we check to see the size of this vector array. And again, this array is just holding unsigned integer values. And these unsigned integer values represent the ID numbers for each of these nodes that is inside the scene graph. So first thing we do is we check to see if the size of this array is greater than 1. If it is, that means there's something already stored at index 0, so we need to replace it. And the way we do that is we go and call add node. We specify we want to add this node transform into our scene graph at the root. So we specify index 0 here. And it's going to return to us unsigned integer ID number, which represents where this guy is inside of the scene graph. We check to see if this is equal to 0. If it is, we know that we have an error message. If it's not equal to 0, we go down here and we go inside of the array, which is holding all of our ID numbers, and at index 0, we save the value that was returned to us from add node. If here this check fails, meaning that this array here doesn't contain any information yet, instead of doing this replacing call here, instead we go and call push back and we specify UI ID here. So everything else is basically the same. We call add node for the transform node that we created at index 0, so at the root, do the check for the error, and then we just call push back. Alright, so that's how we handle the creation of the transform node at the root. Now next thing we have for parsing is the shape node, the light node, as well as the plus sign. Well, shape node is easy because at the root we're not allowed to have a shape node because all shapes have to be nested underneath transforms, which means they have to be processed inside of the if statement here where the plus sign is. So if we found a shape node inside of our testing level, basically if we found something like this, this will give us an error message because this shape is not nested underneath any transform. So that gives us an error. And to handle that, we basically go inside here and we say shape node must be nested underneath a transform node, show the error, and then we reset the error. We can do the same thing with the light. We can't have lights directly at the root. They have to be nested. They have to have a plus sign in front of the keyword light. So if they don't, we just generate an error message saying light node must be nested under transform node, and then we just return. Okay, so we're down to the last thing here. We're parsing the plus sign now. Plus sign is a little bit of work because we need to figure out, first of all, how many plus signs are there. You'll notice here that we could have 1, we could have 2, we could have 3. As a matter of fact, we could have up to a maximum of 32. And 32 is the maximum depth that we're allowed to nest objects under. So what we do is we set a counter up, we set it equal to 1, because we know we've found at least one plus sign already if we've gone into this if statement. We then go inside of this while loop, which is an infinite while loop, but it breaks out whenever we stop finding plus signs. So we go through here and we check to see if the next value inside of the string that we're parsing is equal to a plus sign. If it is, we increment the counter and then we continue looping through. As soon as we don't find a plus sign there, we break out of the while loop. We can also break out if the count value is equal to 33. In other words, it's greater than the maximum depth that we allow. So we just generate a message saying node on line whatever is nested too deep, maximum is 32. And then we return. So by the time we get to here, iCount gives us the number of plus signs that we've parsed already. Next thing we do is check to make sure that the nesting depth is valid, because it is conceivable that, for instance, someone does something like this. If they do this, we would parse through all these plus signs and get to the transform location. But by counting all these plus signs, we'll notice that, okay, we have 1, 2, 3, 4, 5, 6, 7, 8 plus signs, but there was nothing nested under 7 plus signs. So because of that, we can't really work with this transform node because we don't have anything at depth 7, at depth 6, and so on. So to avoid that, we need to make sure we go in and count how many plus signs there are and make sure that the number is valid. So that's what we do here. We check to see if the count is greater than the size of this array that holds all of the ID numbers. Basically, we can go back and inside PaintShop Pro here, using the size of this guy, we know exactly how many plus signs we've processed already, because the size of this indicates the maximum depth that we've gone through. So you see here, if we get a size of 3, then we know we've gone down with 2 plus signs here. So down here, if the count value is greater than the size, then that's invalid because we have too many plus signs. So we just generate an error message saying invalid nesting of node on line whatever, missing node at previous depth. If we pass this check, we can then go and search for our keywords. We have transforms that can be nested, shapes that can be nested, and lights that can be nested. So we're going to go through these in a second. But if we don't find one of these, then we just generate another error message saying unrecognized keyword on line whatever, and then we just show the error message and return. So what do we do inside transform? Well, you'll notice that this code is basically the exact same thing we just finished talking about up here inside this transform. The only difference is anytime we go in and reference the SZ data value now, instead of just passing in 10, we're passing in iCount plus 10. You'll notice here, let me just scroll up to the top, we had transform, and here we have SZ data 10. And then down here we have SZ data 10, because this 10 value represents the length of the keyword transform plus 1. But now we have the length of the keyword transform plus the number of plus signs that were already processed. So we have to take that into consideration with this iCount plus 10 value here. But beyond that, everything is exactly the same. So I'm not going to go through it in any more detail. I'm just going to scroll sort of slowly down through here so you can see what we've got here. Visibility, translation value, center value, scale value, the axis, and the angle of rotation. Alright, and then we go down through here again, where we're going to be using that array to figure out how to nest the transform automatically. So this time we check to see if the count value is equal to the size. If it is equal to the size, then we know we need to add this node to the container in case we need to nest something underneath it later. So in other words, we need to go and call pushback with the ID number that we get back from add node. Now notice this time when we call add node, we're calling it not with 0 here, because we're not nesting with 0, we're nesting with the previous value that's already stored inside of the scene graph. So in other words, back here, whenever we're processing this guy, we need to nest it underneath the node ID that's saved up above. So that's what we do here. We take the count value, subtract 1 from it, get the value that was stored inside of the array at that location, and then use that inside of the add node here. So if these are equal, we use pushback. If they're not equal, then we know we're at some depth that has a value already, so we don't push back. Instead, we just replace. And we replace using the count value here, and we pass in the unsigned integer ID value. And the same thing here, we call add node for the transform that we just finished creating using the value that we pull from the array. Alright, so that shouldn't be too difficult. Now let's go take a look at the shape. Shape node we haven't talked about yet, so we're going to go through this a little bit slower, but the code is very similar to what you've been seeing up till now. We create some variables, a variable here for the name of the shape, the ID number, the material number, the texture ID number, and the texture transform ID number. We look for the required fields, so we're looking for a GeoID, and this time we're passing in the count plus 6 value of the SZ data parameter here, and we're saying we want to return an integer, and the integer we're going to be returning is the address of GeoID here. If the return value is not equal to return OK, then we generate an error message because GeoID is required, so we do need it. We do need that value. Alright, then we start working with the geometry. We create a geometry pointer here, we initialize it to null, and then what we do is we go through our array that we have here, m_v_level param, and you'll remember this is an array of level file parameter values. And if we go back under level file param, you'll see this guy contains an ID number, a type of parameter, as well as the ID number that we're using inside of the scene graph. So this one's the scene graph value. This is the one that the user specified inside of the testing.lvl file. So what we do is we go through this entire array of everything we've stored up till now, and we're looking for parameters that are specifically geometry IDs. So we're looking for the types for geometry IDs. We then are looking for the ID value, which we just got here from the parsing, and we're looking for that same value that's already stored inside of this container. As soon as we find that, then we can go in and extract the ID value that we've saved inside of that container. So we're using .UI ID here. this is going to give us the ID number that was returned to us from the initial call whenever we saved the geometry inside the memory. But we need to call -1 here because you'll remember that the container that we use for all of our geometries are index 0. So we need to make sure we subtract 1, or else this ID value that gets returned here is going to be pointing to the wrong geometry. So make sure you don't forget this. As soon as you do that, we can then get the pointer to the geometry that we need to associate the shape with. So we break out of this for loop here, and then we check to see if our geometry pointer is equal to null. Well, it's only going to equal to null if we did not find a match here according to whatever we're looking for up here. So if that's the case, we generate an error message saying error on line whatever geometry ID number that we wanted here is not found. If we've saved the geometries already, which we should have, because the way we structured this file is we put all of our geometries at the top, all of the materials, textures, and so on, so that by the time we get down to here and we say we want to use geometry ID number 3, we should already have geometry number 3 saved in memory because it was already processed earlier. Whenever we process the grid, cylinder, box, or whatever, you'll see that we save all the information inside of this container here, as well as whenever we call add geometries, or what was the name of that function? Add, was it add? Maybe it was save. Save geometry. As soon as we call save geometry, this function saves data inside of this container here. So everything should be already accessible to us so that we can retrieve the pointers that we need when we need them. Alright, so by the time we get down to here, we should have a pointer to the geometry that we want to associate with this shape. So that's what we do. So we create a new shape node and we pass in the pointer to the geometry which we found up above. If this returns null, we'll generate an error message. Otherwise, we'll continue on down through. Now we go in and call add node. We're going to add the shape node to the scene graph, and the location of the shape node is going to be located at wherever this m_v node ID is pointing to with reference to count -1. This is basically the same thing we did with the transform node, but now we're using this container to store also shape nodes, because shapes are treated just the same way as transform nodes as well as light nodes. Everything is grouped inside of this array here because everything needs to get nested accordingly. So if this returns 0 to us, then we know that add node failed, so we generate an error message, and then we return. Otherwise, we continue on down through. And once again, we check to see if the size of our array here is equal to iCount. If it is, we call pushback. Otherwise, we just go and dereference the value at iCount, and we now save the new shape node's ID value inside of that array here. Okay, so after we've done all this work, we now can go through and look for the optional parameters that are associated with the shape node and save them inside of the shape node. So first thing we look for is the name parameter. We pass in SZData iCount +6 in here. We say we want to return a character string, and we're going to save it inside of this parameter here, SZName. So we pass in the address of index 0. And if it returns OK to us, then we can call pshape setName, and we pass in the name parameter. We do the same thing with material ID. We pass in here we want to return an integer for iMaterial ID. If it returns OK to us, then we have to do a little bit more work. We create a variable here called bFound, and we initially set it to false. We also have a counter here which we set at equal to 0, and then we go through the entire size of this container level param. Again, we're looking for a certain type, so we specify we want to find a material ID, and then the material ID we're looking for is iMaterial ID, which was returned to us up here from this find keyword, and we're looking inside of that container at every single index value underneath the iUser ID. If we find a match, we can then say, okay, bFound is equal to true. We break out of the for loop. And then down here, if we found our material ID, then we can go and assign the material to the shape node, and we pass in the ID number that's saved inside of this container here. So remember, this container is storing 3 parameters for us. It's storing the ID number that the user specified, it's storing the ID number that we're using for the scene graph, as well as it's storing the type of parameter that we've saved inside of this container. Now notice one thing here though. The parameter value that we're getting here, we don't subtract 1 from it. We only had to do that up here when we're working with the geometry. Here, we subtracted -1 because we're dereferencing directly from this container. But down here, when we have a function that does that dereferencing for us automatically for the material pointers. So we don't need to subtract 1 from this parameter value here. If the material was not found, then we generate an error message saying that this specific keyword that we're looking for, material number that we were looking for on the specific line is invalid because we couldn't find it inside of the container. Alright, and now notice that here I did not return out of this because technically if we don't find the material, it's still okay because the material that is going to be used is the default material, which is sort of that gray color. So it doesn't really matter if we don't find the material that the user specified here, but I still do generate the error message and I show it to the screen so that you can go in and fix the error inside of the text file. Alright, next thing we do is we look for the texture ID. Again, same sort of process. We pass in that we want to return an integer, and we're going to save it inside this value here. If we find it, we go in and look for all the textures to find the matching texture ID value inside of this container. If we find it, we then go and assign the texture to this shape, and we pass in the ID number for the container that we found up here. If we don't find it, we just generate an error message saying cannot find this specific texture. Oh, I guess this should really be texture ID here. And then show the error message onto the screen and continue on down. The other thing I forgot to mention is anytime that you do get a duplication, this is confusing, so you don't know which one you should be using. So I do stop and go and return out of the parsing, as well as I go and call safe delete for the specific shape. Okay, so last one here is texture transform ID. And again, same process. We want to return an integer. It's going to get saved inside of this value here. If the return value is okay, we go looking through this container for all texture transform ID numbers. We're looking for the match here between user ID and the texture ID that was returned to us. And if it's found, we go and assign texture transform to this shape, and we specify here is the ID number to the nested transform that should get associated with the shape. Otherwise, we go and specify, we have an error message, and again I have that same bug here, so we'll just go in and fix it. Let's replace that there, and replace this texture transform ID not found. Here we can replace this with texture ID not found. Okay, and that's it for the shape node. So now we're left with one more if statement here. We have if we're looking for lights, lights that are nested. We create a bunch of variables to hold all the values for any lights that we may be importing from the file. We check first for all the required fields, so there's only one of them, and that's the type. So we say, okay, we want to look at SED data from iCount +6 onward, and we want to return a character string, and we're going to save it inside of this type parameter. If it returns to us successfully, we then check to see if it's a point light, a directional light, or a spotlight. If it's neither of these, so if it's not equal to 0, we do str compare, so this is a C++ function to do a string comparison between this string and this string here. If these are equal, it's going to return 0. If these are not equal, then it's going to be either +1 or -1, depending on which one's greater than the other. But that doesn't really matter, so we're just going to specify if it's not equal to 0, meaning it's this value that we do find inside the parser is not equal to point, then this would return true. And if this one returns true, and if this one returns true, that means that it's neither point, directional, or spotlight, then we generate an error message saying that this specific type is an invalid light type on line whatever this line number is currently on. Otherwise, we continue on down through here. So what we can do is we can create a pointer to a light. We then go down here to this if statement, and we know we need to do a branch because we're going to either have a point light, a directional light, or a spotlight. And each of these have to be handled slightly differently for a couple parameters. So if we're using a point light, so if point was specified inside of the testing.lvl file, we're going to go into here. If instead we had directional, we're going to go into here. And if instead we had spotlight, we're going to go into there. So we have if, else if, and then else if a third time. So the first one, if it's a point light source, what we're going to do is we're going to create a pointer to a light point. We then call new light point. We specify the renderer because it needs that as an input parameter. And we check to see if we have any errors. If we don't have any errors, we then start parsing all the things that are specific to a point light source. So we know we can have attenuation with a point light source, so we look for a 10. We specify here I count plus 6, and attenuation is going to be 3 floating point numbers, so we specify float array 3, and we're going to save it inside of this variable here. If it returns OK, we can then go and call, for this point light source, set attenuation, and the 3 values we're going to call by creating a vector 3 with the 3 values that we returned here inside of this variable. We do something similar for the position of the light source. We say we want another float array 3, we save it inside of this array, and if it returns OK, we go and call set position. And again, same thing, we create a vector 3, position X, position Y, position Z. And then what we do is we say, okay, this pointer to a light is going to actually equal this pointer to a light point. So down here we're going to say these two are equal. So this pointer is now pointing at the point light source. You'll notice that P light is a pointer to a light and P point is a pointer to a light point, but we can equate these two because light point is inherited from a light. So in the compiler's point of view, these two can be considered equal. So that's why we're allowed to do this. And then we go and process the other optional parameters which are generic to all 3 light sources. But before I talk about those, let's go and finish off the directional and spotlight first. So under the directional light source, we create a light directional pointer. We call it P directional. And again, we call the new operator for light directional. And we check for the direction this time because point light source doesn't have a direction, so we didn't need to do that. But with a directional light source, we do have a direction. So we look for the keyword directional. We're looking for 3 floating point numbers. We're saving them inside of this array. And if it returns OK, we go and call set direction, specifying X, Y, and Z for the directional light source. And then once again, we're setting the light source's pointer to the light directional pointer here. Lastly, we have the spotlight. It has a few more parameters than the other ones because it's a little bit more complex. So we create a pspot value here, which is a pointer to a light spot. And we check for attenuation, same as we did with the position here, array 3. We save it inside here. If it's okay, we just call set attenuation with linear, constant, and quadratic. We check for position as well, same as we did with the point light source. So we save the position value here, and then we call set position x, y, and z. And then we have direction light with a spotlight as well, so we need to call the keyword search here for the floating array 3. And once again, we're saving set direction, this time x, y, and z here. Now we also have a cutoff angle, so we need to go and return a float for f cutoff. If it returns OK, we call set cutoff. We look for an exponent value as well, floating point number with f exponent as the parameter. And if we return OK, we call set exponent. And then the last thing again, we set the spotlight's pointer equal to the light pointer over here. So once we get out of this if statement, we now are working with just P light, because P light could be either spotlight, point light, or directional light. So knowing that, there's a couple extra parameters that are shared between all 3 light sources. One of them is on. So we check to see if we have an on parameter that we need to parse. So, and on will be an integer, so we pass in here ion and return int. If it's okay, we then call set on equal to whatever this value here returns. So we check to see if ion is greater than 0. And if this is the case, then it's going to return true, which gets set into this function here. Otherwise, we pass in false, which gets passed into set on. We look for the ambient color. It's a float array of 4. We save it inside f4 ambient. And if we did have that parameter, then we'd go down here and call set ambient color, and we pass in the red, green, blue, and the alpha value inside color OpenGL, which then returns the value that gets passed into set ambient color. We do the same thing with the diffuse light, or sorry, with the diffuse color, and there it is there, f4 diffuse. And to set the color, we call set diffuse color, same thing, red, green, blue, alpha. We have the same thing for specular color, array 4, f4 specular. And we call set specular color for red, green, blue, alpha. And then we're ready. So we have all the parameters inside of this P light already specified for us. So we call add light, and then this will save this specific light source inside of memory so that it can get cleaned up automatically whenever we quit our scene. Now what we need to do is create the node light pointer, which is the pointer that we use to nest things inside of our scene graph. So we call new node light, and we pass in the light source which we just finished creating. Again, if there's an error message, we generate an error. Otherwise, we'll go and call add node, and we add it underneath the location here. Same thing that we did for the shape node and the transform node. And then we also have to check the size of this container here to know if we have to push the light source's ID number or whether we just replace the light source's ID number with whatever is currently located at iCount. And we also have an optional parameter here. We could name the node light inside of the scene graph. So if that's the case, we parse the name. We say we want to return a name here. And we then call set name for the name that was returned here of the light node that we just finished creating. And that's it. So after all of that, we should now have an automatic technique to parse our testing LVL file and create the scene graph according to the structure that's actually associated in here. So let's go and try compiling this. And I bet we're going to get a bunch of error messages because writing all this code without testing it systematically, well, you can generate lots of error messages. Let's see, what do we have here? M_F4 emissive is not a member of material. Oh, right. One of the messages on the forum, you'll notice that I mentioned that I've actually misspelt emissive inside of the material node. So if you go in here, and if you haven't changed this already, you should go ahead and do this. Emissive here, 1 M, 2 S's, not 2 M's, 1 S. So if you rename this guy, and then save that guy, we can go into here, and anytime we use emissive, just rename it, and that should get rid of those error messages here. And let's see, we have a couple more things here. Cannot convert vector 3. Alright. We have 3 constructors for vector 3. We have either a null constructor, we have one that you pass in a vector 3, or one that you can pass in an x, y, and a z value. So F3 translate is actually 3 values, so what we need to do is do something like this instead. X, Y, and Z. And looks like we'll have to do this a few times. For all the different parameters that ended up getting passed in this way. So just bear with me while I correct this. Okay, another one here. Another one here. Scale also needs to be updated. The other option you could do is to possibly simplify your life would be to write another constructor that allows you to pass in a pointer to an array and then change it to one location rather than doing what I'm doing here. But I'm almost done now, so if I had more than these, I probably would have done the second alternative. Okay, let's try this now, see what we get. Okay, that built, surprisingly. And we got some more things here. Okay, emissive, again with the misspelling. Okay, there we go. Now, one other thing is there were a few other things that I noticed while I was working on different videos, and I posted comments on how to fix these bugs in the forum, but I wanted to go through in this video, since we're cleaning up some things now, we might as well go in and clean up these other things that I found recently as well. So let's just start off by doing the following. Inside scene, here we have assigned material. You'll notice here that if the material ID value is greater than the size of the material, then we generate an error message. Well, we can also conceive that an error could happen if, let's see here, if this or this number here that gets passed into us is actually 0. If this is equal to 0, then this is also an invalid material ID number, so we want to generate an error message. It shouldn't happen, but I just wanted to add this extra condition here because with the extra parsing we just introduced, it is sort of possible that we could get a material ID number of equal to 0 happening. Same thing could also happen under the texture and the texture transforms. So we'll just go in here and add in the extra check to make sure that texture ID cannot be equal to 0, and the other one was texture transform. Or texture transform equal to 0. Okay, so add those 3 extra checks in there. The other thing is underneath scene update, this was a nasty bug that took me almost a day to find, but it's terrible because it's really a simple thing that I just missed. Make sure that you have GL matrix mode specified before you call GL push matrix as well as before you call GL pop matrix. So earlier I didn't have these 2 lines of code in here. Make sure you add them inside your code. Anytime you do a push and a pop, make sure you always specify what matrix you're going to be pushing and what matrix you're going to be popping. Because if you do some extra work up here and for whatever reason you didn't reset your model view matrix properly, you could be pushing and popping the wrong value. And a little bit later on in the videos, what I was doing is I was working with some stuff in here which actually reset my model view matrix to be not the current one that was active. So I was popping things from the matrix stack, but I was thinking it was the model view matrix, but it actually wasn't. It was the texture matrix, which ended up throwing everything off in my program. But the strange thing was, it would run for a little bit and then it would stop running, and that's why it took me so long to figure out the bug. I finally narrowed it down by creating a method to show me how many frames I'm actually able to render, and I noticed that it was only rendering 32, and I know that the matrix stack is maxed out at 32, so I knew it had to be something to do with this pushing and popping. And once I started looking into the code, it became obvious that I wasn't specifying model view matrix here, so because of that my program was crashing. If you go in and add these 2 lines of code here, you won't have any problems later on, so I strongly advise you do that. And as a matter of fact, what would also be very helpful is if you go in here and do a search inside your entire solution for GL push matrix. Anytime you find GL push matrix, make sure you have your matrix specified. So here we have model view matrix specified before we push, and down below here, whenever we're popping, we say put model view matrix back. Well, make sure you specify you want to pop the model view matrix. So add that line of code there. Let's see if we have any others here. Here we're pushing model view matrix. Right here we're popping, so specify your popping model view matrix. This will just save you a lot of headaches later on. Here's another one that I missed. Pushing, we're pushing the texture this time, and here we're popping the texture, so that's okay. Here we're pushing the model view matrix, and here we're popping and we specified it, so we're good. And 2 more. Here, oh, and these are the 2 that we've already just fixed. This one, pushing here, popping here. And this one, oh, here we go. With the house, we're pushing the house and then we're popping it at the bottom. Well, as a matter of fact, we might as well get rid of the house because the house is no longer supported with our current game engine. So just to clean up a few other things, inside the object lib, we can go in and delete house.cpp and triangle.cpp. You don't need these anymore because they're no longer supported with the whole scene graph structure. So to avoid getting confused in things, just remove them from your project. You won't need them anymore. As a matter of fact, you can go into your code where all these files actually exist and just delete them. You're not going to need them. Let me check my list here, see if we have Anything else? Oh, right. Here's something that was kind of annoying. Underneath source, where was it? Inside main, we have stdafx.h. And if we scroll down to the very bottom, no, it doesn't look like this is... Oh, right. I don't think I actually implemented this. Let me check. Did we create a variable called pi anywhere? Later on, I work with a lot of rotation matrices, and I need the value of pi. But it looks like we're okay here, so don't worry about that. I guess I didn't introduce that bug here. One other thing, inside of the scene, the destructor. Inside the scene destructor, we call clear all. Clear all is right here. Make sure you have all these in here. I noticed that earlier I was missing a few of these delete. I actually created the delete alpha objects, but I forgot to add it in here. And I think there's one other one that was missing. So just make sure you have all the delete all functions inside of the clear all. If you're missing one, you could potentially get a memory leak if you're using that specific item. So have alpha objects, fonts, geometries, lights, materials, nodes, textures, and texture transforms. Basically, what you should find in here should correspond to all these vectors here that you create and use to store everything inside of the scene graph. All of these you should create dynamically by calling either add font, add light, add node, or assign. As soon as you do that, it's going to save values inside of these containers. Once you have values saved inside of these containers, you need to make sure you can clean them up whenever your program stops running. So whenever your destructor calls, it calls clear all. So it should call all these guys. If you're not calling them all, you're going to have a memory leak. Alright, so let's go and now close all those guys off. Just rebuild this one more time. Make sure everything is fine. And we can, I think, run a test now. Let's just go and take a look here. What do we have? We have, well, I generated a scene here. And let's run it to see what we have. There we go. We have a general scene. Looks like we have our box rolling in behind us. And in front of us, we have a couple barrels and some boxes lined up all on the side. Now, the nice thing is, what we can do is we can go inside of our code where we have this here. We just finished building and creating this project here. So we have the current build. If we again run this, there's our barrels and there's the box that's rotating. Well, notice now we can go inside of testing.lvl. Let's just send this to our text editor. And I can go in here and change things dynamically. Let's say, oh, I don't know. We have some end crates here. Let's say we wanted some more crates for whatever reason we want. Okay, let's go and go in here and create 2 more crates. And these 2, let's say I don't want them nested that far. Let's say I want them over here. And let's just move them off some really far distance so we can see we're actually creating these crates. So one at -5 and one at +5. Save that. Now we can go back and rerun the program, and notice those 2 crates have just been created. They've been created dynamically. You notice that how quickly I was able to do that. I didn't have to go through and recompile my code. Here it's saying that testing LVL has been updated because it was updated through context, not through Visual Studio. So it just asked me to update it, and here's the new updates. So you notice with the with the testing.lvl file, we're able to do a lot of modifications to the way that the scene looks visually without actually having to go and recompile. So you can go in here and actually start creating 3D worlds just using a text editor. And because we created our parser reads in this file and it creates the scene graph automatically for us, and then generates all the code that's needed to link everything together. So there we go. Parsing 101. It was a long video. I think this was one of the longest ones I've done so far. I feel like I'm losing my voice, but we're through, we're done. We don't have to ever look at this code again. Well, that's not really true. We're going to come back here and start adding extra features in here once we get the time to. But now you can see the power of parsing. With a text parser, you can change things dynamically, and you don't have to rebuild your code to make your changes visible inside your game engine. Next video, I'm not actually sure what we're going to be covering next, so I guess I can't tell you what to expect. Keep an eye open on the website under the forums if you have any problems, or if you do have problems, feel free to post messages asking about details or whatever. I did kind of skim through a lot of this code because it was very repetitive. So if there was something that wasn't shown on the screen that you need to know how to do because you can't get your code running, feel free to drop a message off on the community forum, and I'll fill in the details. Have fun with the text parser, and once you get your engine up and running displaying different things, post your testing.lvl files on the community forum and show off what you can do. I'm interested to see what kind of 3D shapes and 3D geometries you guys can put together, or basically levels, really. What kind of scenes can you put together with the existing engine?